Hello, my name is Huami Jie and I'm from Car Minds, which is a car robot and services company. It's a video about our research on the body-gesture interaction in human-robot conversations. The motivation of our work is that we found current humanoid robots are already capable of giving fair verbal responses during their communications with humans. However, their body gestures are still somewhat unnatural. So we started to think about the question, can robots exhibit more realistic body gestures, just like our human does? Let's first look into the body gestures in a real human conversation. When two people are talking, both the speaker and the listener use body gestures. For the speaker, body gestures are as an assistance for what he's saying, and for the listener, body gestures are as a nonverbal feedback to the speaker. Based on this observation, we proposed the two models, the listening model and the speaking model, taking different signals as input to help robots generate proper body gestures in both speaking and listening phases. Considering that the body gesture can be regarded as a sequence of body poses, we came up with an idea to formulate the body gesture generation problem as a sequence mapping problem, just like the machine translation and the conversation modeling, which map a word sequence to another word sequence, and the video caption, which map a frame sequence to a word sequence. We can generate the body gesture by mapping a word sequence altogether with a pose sequence to a pose sequence. Inspired by the great success of sequence-to-sequence architecture in the sequence mapping problems, we also adopted this framework in our experiments. The main idea of sequence-to-sequence is to use an LSTM layer to encode the input sequence and another layer to produce the output sequence. As we can see, in the speaking model, the encoder contains only one LSTM layer for modeling the speaker's on-word sequence, while in the listening model, there are two parallel LSTM layers for modeling the speaker's word sequence and pose sequence. The two branches will be fused by element-wise addition before the decoder. However, the raw data of words and body poses cannot be parsed by the network, so it's necessary to encode them to numerical vectors. We can easily embed each word to a vector by mainstream word embedding algorithms like word2vec or BERT, but the encoding of body poses is much more complex. We represented body poses by 3D key point skeleton. In our experiments, we used AlphaPose to get 2D key point coordinates and then lifted them into 3D space. Note that we only selected 12 upper body key points. There are two reasons for it. First, we found that in many training videos, people's lower body was often invisible, which leads to many missing values in the training data. Second, in human conversations, body gestures are mainly performed by the upper body. So, we focus on the 12 upper body key points and store their 3D coordinates in a 3x12 matrix, with each column containing the coordinates of a single key point. However, we can see that the extracted 3D key points are sensitive to the camera perspective, which means the same pose may look different from a different perspective, resulting in different representations. To avoid this ambiguity, we rotated all the skeletons around the z-axis to make them all face the same direction. Specifically, we hope to equalize the y-coordinates of the left and right shoulders after rotation. To this end, we first constructed a vector from right shoulder to left shoulder, then projected this vector on x-o-y plane and got the angle between the projection and positive x-axis. Finally, we calculated the multiplication of the basic rotation matrix by the former key points matrix to get the rotated matrix. The rotated key points still involve absolute scale and position information, which is irrelevant to the definition of body poses and should be eliminated by the feature normalization. We tried several normalization methods in our experiments. It's a common idea in many single-frame algorithms to normalize each key points matrix individually. Basically, for each matrix, we found the maximum and minimum of x, y, z respectively and perform min-max feature scaling along each axis. As a result, all the values in the matrix were brought into the range of 0 to 1. However, this normalization method is not suitable for sequence modeling. For example, suppose it's a normalized key point skeleton at frame t. In the following frames, the person moves his left wrist. What will happen to the normalized features? Since the normalized x-coordinate of left wrist already reaches 1 at frame t, the individual normalization will squeeze all the x-coordinates to keep the left wrist staying at 1. As a result, the normalized x-coordinate of the moving key point keeps unchanged, with that of other still key points being squeezed. A solution for this problem is to use global maximum and minimum of x, y, z instead of individual ones. As we can see, the global normalization correctly reflects the actual key points movements in the normalized features. Apart from the above two methods, we also tried another idea to break up the entire skeleton and reconstruct feature vectors from adjacent key points. The inspiration is that we found the body gestures are essentially about the movements of limbs connecting adjacent joints. So we try to use vectors between adjacent key points instead of coordinates to encode body poses. Here is the illustration in 2D space. We reconstructed 12 vectors by setting belly as the origin and connecting 11 pairs of adjacent key points. After that, all vectors are normalized to unit length and reorganized to form a new key points matrix. We also considered to represent each vector in angular space instead of Cartesian space. However, we found that the angle of closed vectors around positive x-axis are discontinuous, which makes the network hard to converge. This issue is also identified in 3D space. After the signals encoding, we need to feed data into our network. We first flatten the normalized 3x12 key points matrices to 36-dimensional vectors, thus represents the body gesture as a vector sequence. However, if each key points vector is passed by an LSTM unit, we require a very long layer to process all the vectors. As we know, the overlap of LSTM layer makes it hard for training. So we pack several consecutive vectors in one vector to reduce the demand of LSTM units. Now comes a new question: how to choose the number of vectors in each pack? Recall that in listening model, we encoded body poses together with the words, so we hope to model the two signals with the same rate. Statistics shows that the average speaking rate is 0.4 seconds per word, as the video is captured at 25 fps, so one word approximately lasts 10 frames. Therefore, we concatenate every 10 key points vectors in one. Thus, each packed vector is of 316 dimensions. On the other hand, the word embedding model is fine-tuned to embed each word to also a 316-dimensional vector for the convenience of feature fusion. To train our models, we need substantial videos of human conversations. We found talk shows like The Ellen Show and Tonight Show meet our requirement perfectly. So we downloaded these videos from YouTube and pre-processed them to make our dataset. Basically, each video was segmented into several clips depending on the current speaker. Then the speaker's word sequence and pose sequence, together with the listener's pose sequence, would be extracted. To train the speaking model, we take the speaker's word sequence as input and pose sequence as ground truth. While to train the listening model, we take the speaker's word and pose sequences as input and the listener's pose sequence as ground truth. During the training stage, we adopted mean square error as the loss function. And to evaluate the performance of our models, we adopted both MSE and cosine similarity as metrics. We compared three normalization methods in both speaking model and listening model. As shown in the figures, the vector normalization method outperforms the others under both metrics. Here are some examples of the body gesture generation. It can be seen from the results that both the speaking model and the listening model fit the data very well. That's all. I hope the video helped you better understand our research. Thank you very much for your attention.